Okay, so now we will talk about the classification of subgroups of cyclic groups. And this theorem says the theorem is fundamental theorem of cyclic groups. It's very important result, very amazing result, tells you everything about the cyclic subgroups. So the main thing is every subgroup of a cyclic group is cyclic. Perfect. Moreover, if you have a set generated by A and its order is n, then the order of any subgroup of the set A generated by A is the divisor of n. Very good. And for each positive divisor k of n, the group which is generated by A has exactly one subgroup of order k, namely the set generated by A power n quotient k. Perfect. Now, before proving this theorem, which we will not prove in this lecture, we will because it's a very long proof, and then you can refer any text for the proof. I'm just going to talk about its applications and its understanding. So, so suppose G is a G understanding, I should say here, of theorem 4.3. So, say this is the topic, and we are saying that G is a set subgroup is a group generated by this A, and order of G is 30. Perfect. Then the first and second parts of the theorem says that if H is a subgroup of G, if H is a subgroup of G, then H is actually as a group which has the form 30 divided by K, giving that for some K that is divisor of 30. That is divisor of 30. So the first two parts, first and second part of the theorem says this, that if H is a subgroup of G, then H can be written as it has the form A generated by the power of 30 divided by K, given that K is a divisor of 30. The third part of the theorem says G has one subgroup of each of orders. Now, if you write the divisors of 30, the divisors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30 itself. So, so G has exactly one subgroup of these orders. That is the power of this theorem. Once you know the order of a group, then you know the orders of the subgroups. How fascinating that is. It's an amazing result. That means what we are saying, that the list of subgroups of G, the list of subgroups of G is what? That is, first, it is equal to G itself, that has order 30. Second, you can write something like A square, which will have elements E, A square, A power 4, and A power 28. This is order 15. Then you can write AQ, and that is E A cube A power 6 up to A power 27. This is order 10. Then you can write something A power 5, which has E A power 5, A power 10 up to A power 25. This is order 6. And similarly, you can go on. The list will have A power 6 with order is equals to 5, A power 10 with order is equals to 3, A power 15 with order is equals to 2, and A power 30 itself, which is just the set with element 1, so it has order 1. Perfect. Now, in general, if A has order n and k divides n, then the set generated by A power n minus k, n over k, is the unique subgroup of order k. So that's what we are saying. The corollary, let's present the corollary. Says that subgroups of Zn the statement is, you take for each positive divisor k of n, the set generated by n over k is the unique subgroup of Zn of order k. Moreover, these are the only subgroups of Zn. Perfect. So if you have the set, the group Zn, then the divisors of n, which are denoted by k at this time, are going to give the subgroups of that Zn. Perfect. So similarly, the example 7, which we is that the list of subgroups of Z30 is what? We know the divisors of Z30, so the list is 1, which is 0, 1, 2, 29, order 30, 2, 0, 2, 4, 6, 28, 3, 0, 3, 6, 9, 27. This has order 15, this has order 10, and so on. We have 5, we have 6, we have 10, we have 15, and we have 30 itself. And you can imagine the elements in them, and the orders have, this has 6, this has 5, this has 3, this has 2, and this has 1. So this is the list of elements. You can fill them up yourself. Okay, perfect. Now let's try to find generators of the subgroups of order 9 in Z36 using theorem 4.2 and 4.3. So the example 8 is about to find generators of the subgroup of order 9 in Z36. What we observe? First, we observe that 36 divided 9 is 4. 36 divided by 4 is one generator. To find the others, we have from corollary 3 of theorem 4.2 that they are all the elements of 36 of the form 4 into j, where GCD of 9 and j is 1. So thus, let's say is one generator. To find others, we have from, if you go back to corollary 3 of theorem 4.2, that they are all elements of Z36 of the form 4J, where GCD of 9 comma J should be 1. So thus you can write that will be 4 into 1, which is also 4 into 2, which is also 4 into not 3 but 4, which is also 4 into 5, is also 4 into 7, and 4 into 8. Now okay, perfect. Now in generic case, find all the subgroups of A of order 9, where order of A is 36. We have, so to find all the subgroups of A, of the set generated by A of order 9, where the A itself have order 36, we have what? We have that it will be the set generated by A power 4 power 1. It will be the set generated by A power 4 power 2, set generated by A power 4 power 4, the set generated by A power 4 power 5. Similarly, the set generated by A power 4 power 7 and A power 4 power 8. Okay, so in particular, note that once you have the generator A power n over D for the subgroup of order D, where D is the divisor of the order of A, all the generators of A power D, the set A power D, have the form something like this. So let's write that in a abstract way. In particular, note that once you have the generator A power n over D for the subgroup of order D, where D is a divisor of the order of A, which is n, all the generators of A power D, say generated by A power D, have the form A power D power J, where J belongs to U of D, which means JCD, which means GCD of 9, sorry, GCD of D and J should be 1, because all the elements of in U of D are going to be these elements. Okay, and that is the That is how we find all the generators. Okay, perfect. Now, by combining theorem 4.2 and 4.3, we can easily count the number of elements of each order in a cyclic group. And for convenience, we introduce an important number theoretic function called Euler-Phi function, which says that Euler-Phi phi or phi function says that let phi of 1 is 1 and for any integer n greater than 1, let phi of n denote the number of positive integers less than n and relatively prime to n. In other sense, all those elements which have GCD with n is 1. And notice that by definition of the group, U of n by definition of the group U of n says that order of U of n is going to be phi of n. So in U of n, we store all those elements which has GCD with those elements equal to 1, but the phi of n counts the number of all those elements. That's the difference. So first 12 values of phi of n are given in the table. So you can say first 12 values of phi of n are given. So let's say we have n here and then phi of n here. 1 will have 1, 2 will have 1, 3 will have 2. How? So if you say u of 3 will have elements 1 and 2. So that's why phi of n is 2. Then 4. 4 will have 2. Again, 1 and 3. 5. 5 will have 4. Again, 1, 2, 3, 4. And then 6. 6 will have 2. 7 will have 6. 8 will have 4. 9 will have 6. 10 have 4. 11 have 10. 12 have 4. Okay. Perfect. So there we will end this lecture. Thank you so much.